Kepler's Third Law concepts. Kepler's Third Law is typically written as an equation. A cubed equals p squared. But what do those symbols mean? Well, recall that a planet orbits the sun in an elliptical orbit that looks a lot better than that picture. So here's our sun and the orbit of a planet. Because the distance to the sun changes, we don't have one set number for the distance to the sun. So A is what's called the semi-major axis. And that's half of this long axis of our ellipse. We can think of that conceptually as being essentially the average distance to the sun. So this side of our equation is talking about how far is the planet from the sun. The other side of our equation, the p squared, p is the orbital period. So this is basically a planet's year. How long does it take to go once around? So what the equation is telling us is that there is a relationship between the distance a planet is away from the sun and the time it takes the planet to orbit the sun. So our general rule of thumb is the farther a planet is from the sun, the longer it takes to complete one orbit. And, that really does make sense, because if you're farther from the sun, you've got two things working against you. One, the orbit is going to be a longer distance. That is, you have to travel a longer distance to make your way all the way back to where you started, because you're going all the way around. If you're close to the sun, your distance is a very short path to make one complete circle. If you're farther from the sun, your orbit's bigger, you've got a longer path to follow. So you've got that working against you, so that's one reason why it takes longer. And the other is, the farther from the sun, the slower a planet moves. So not only do you have this long distance, but you're moving slower too. So it's going to take longer to go one complete trip around the sun. A couple things to notice. There are two things that are not mentioned in this law. Mass of the planet doesn't matter. So if you took Jupiter and put it in Earth's orbit, it would take Jupiter 1 year to travel around the Sun. So the fact that Jupiter is much more massive than the Earth won't have an effect. Now, there is a kind of parenthetical, as long as the planet is much smaller than the star. Because this rule works for anything orbiting anything else. It works for two stars orbiting each other. And so when you've got two stars where they are much closer to having the same mass, mass will matter. But for planets going around the Sun, planets going around other stars, the star is going to be much, much more massive than what's orbiting it. And so we don't worry about the mass. Also notice, distance only affects the year for a planet. Say a planet's year. That is the time for one orbit. But not a planet's day. That is the time for one rotation on its axis. If you look at the rotation rates of the planets, they're all over the place. If you look at the rotation rates, Mercury, it's about 59 days. Venus, 243 days. Earth, 1 day. Mars, almost 1 day. It's like 40 minutes longer. So for all intents and purposes, 1 day. Jupiter and Saturn, about half a day. Takes Jupiter a little less than 10 hours. Takes Saturn a little bit more than 10 hours. Half a day, not days. Uranus and Neptune, about 3/4 of a day. So you see that there is no real trend here with distance. We've got these two guys really long. These two really short. And the rest are almost identical. And so you can't say, oh, well, if it's X distance from the Sun, it's going to rotate in this many days. It's all over the place. So we start long, get even longer, get short, about the same, shorter, shorter, longer, longer. It's just all over the place. A lot of things affect planet rotation. Collisions. Collisions can change the direction of rotation, can change the speed of the rotation. The Sun is one reason why Mercury and Venus are so slow, because its gravity is slowing them down. If you have a moon, that can make an effect. In the case of our Earth, Earth's rotation is slowing because of our moon, because of tides. So lots of things go into this. Mass does have an effect because of conservation of angular momentum. The more mass you pull in, the quicker it will rotate. So all of these things can affect the rotation rate of a planet. But for the most part, it has nothing to do with how close it is to the Sun, with the exception of Mercury and Venus, because of that gravitational locking that has slowed them down. But everybody else, it's a lot of different factors, but not the distance from the Sun.